Welcome to CMA's lecture on transmission electron microscopy for material science. In this video, we will review the main aberrations that are relevant to understand the imaging properties of a transmission electron microscope. You remember from the last lecture, we had this graph that shows you and tells you that the microscope has its resolution limited by aberration. Actually, the most important one is the spherical aberration, and we will start with it. So, spherical aberration, you probably remember it from your lecture in optics. And first of all, it's characterized by its coefficient, CS, given in millimeter. And then it tells us that rays that enter the lens away from the optical axis are more focused. That's the case for a positive CS. How does it look like if we try to draw this information? We have here a lens, and we will take some rays that will enter the lens, all parallel to the optical axis. There we have. Normally, such rays should be focused to the focal point of the objective lens. So, something like this, and all the rays coming through the same point. But now, we say that rays that enter the lens away from the optical axis are more focused. So this one is further away, so the lens will be stronger and the ray will be more deviated. And that continues holding for the next rays, which will be even more deviated. Then we should draw this in a symmetrical manner. And finishing the drawing, obtain something like this. That's what you are used to in optics. But now, generally, in a transmission microscope, we are working with very small specimen parts. So you can consider that everything comes from the same place on the specimen. What's the effect now if we take a point object? Let's take the same setup, but our object is now a point. I first need to find a place where the image will be formed. For this, I need to imagine an extended object and draw its image by the lens. This gives me the position of the image at that point on the optical axis. That's where the image of this point object should be. Now, our point object will emit rays in different directions that will hit the lens. Those rays will be focused by the lens to the object point. But the problem is that rays that are further away from the optical axis will see a stronger lens and be focused closer to the lens. It's symmetrical and is even worse for the further rays. You see that the image of a point is not a point anymore, but a disk, and somewhere on the optical axis I have the place where my disk has the smallest possible size. It's the disk of least confusion. This will blur the image and eventually make some kind of strange effects, like the one we will see on the next slide, which show real electron microscopy picture. Typically, the CS will make two effects. On one side, it's able to create ghost images of strongly diffracting specimen. And you see there that you have the actual image of this small crystal, but also like a bright image on each side, left and right. That's what we call ghost image, and this can be obtained due to the CS. It will also blur interfaces. Here we have defects in a crystal, which should be only extending over one atomic layer in this high-resolution image. But if you look at it, you have the feeling that it's extending over 4 or more atomic layers. These two effects are called delocalization. You will see this one in the lecture about imaging with diffraction contrast, and this one will be discussed in the lecture about phase contrast. The next aberration I want to discuss is the so-called chromatic aberration. Again, probably you know it. It's characterized by its coefficient Cc, given in millimeter. And in that case, it tells us that electron at lower energy or longer wavelength will be more focused by the lens. Again, let's try to draw this. I have there my lens, and I will start this time with a simple point object and the two focal point. Again, I should have the image of that point at the same place than I had before. Now I will consider electrons which have the nominal energy of the electron beam, and I will draw them in blue. They will enter the lens, all with different angles, and I will neglect the spherical aberration. So all those rays will be focused to the same point properly, like it should be by a perfect lens. Finishing the drawing gives me the following: a nice point image for nice point object. But now I also have electrons with lower energy. I will draw them in red. They will follow the same path between the object and the lens. But then we say that electrons at lower energy are more focused. So those one will see like a stronger lens, and same for the one which are there, and the one which are at that point will also see a stronger lens. Again, I neglect the spherical aberration, which means that still my point object gives me a point image. Altogether, I will again end up with a blurred image. This also results in a disk of least confusion and therefore blurring of the image. Fortunately, the chromatic aberration is less important than the spherical aberration, for several reasons. First of all, the small energy spread of the probe, especially if you use a special monochromator that will even reduce the energy spread of the electrons coming out of the gun, will reduce the impact. If you use thin specimen, your electron beam will not interact too much with the specimen. So the electrons will not have too many events that will lead to energy loss, and they will keep the nominal energy of the beam. So thin specimen will also reduce the impact. Like for spherical aberration, for chromatic aberration, it is in principle possible to develop correctors, but they are only developed in very few labs, and it's still a research area, while spherical aberration correction exists nowadays on commercial instruments. It's important to consider it at very low tension, but also if you want to analyze the energy loss by the electrons, and this will be part of a later module. A short historical note on these aberrations: chromatic aberration and spherical aberration. Actually, they were recognized to be very important and limiting the resolution of the TEM already in the 30s by Otto Scherzer. If you look at this paper published in 1936, what Otto Scherzer tells us is that you cannot avoid spherical and chromatic aberrations for lenses with cylindrical symmetry, and that they will limit the resolution of the microscope. And the same Otto Scherzer has proposed only 11 years later some solution for this. And one of them is to break the cylindrical symmetry. But building such a piece of equipment was so challenging and so difficult that the first successful correction of a TEM came only in 1997. So now we are remaining with only one aberration, and this one has a slightly different position. It's called astigmatism. Astigmatism is when the focal length is not the same for two perpendicular directions of the lens. Therefore, we need to represent astigmatism in a 3D drawing, which will make the drawing a little bit more challenging. Astigmatism affects all electron lenses because of inhomogeneities in the material or machining, but also because of dust particles that escape the specimen, contamination on aperture or pole pieces, or even because of the specimen itself if it's magnetic. But I have a very good news. It's that astigmatism can be corrected, and that's even one of the important steps that you are doing when aligning a transmission microscope. But let's look at it in more detail. First of all, I have my three-dimensional lens with the vertical direction and one horizontal direction. So I really have to enter the third dimension. This is the optical axis. I will again take a point object which has as an image a point image. Let's start with imaging that we have there, the image obtained when I have rays that enter the lens on the vertical axis. And now we said that the focal length is not the same for two perpendicular directions. If I take rays that enter the lens on this perpendicular direction, they will not focus at the same point. So maybe after, maybe before, depending on how the astigmatism is going, but not at the position where it should go. And it will look a little bit like this. It's more difficult to imagine what's really going on there, because that means that my image, if I look at this plane, is sharp in the vertical direction, but completely unsharp in a horizontal direction. So let's try to see what's going on a real transmission electron microscopy image. And I've taken the simplest case of a hole that is there, so I have no specimen in the inside, and which is in a carbon film. So that's amorphous carbon. If everything works well and if my image is in focus, you see very well the rim of the hole with no particular contrast. If I now overfocus the lens, I will see some strange contrast there, which look like grains appearing in the carbon film, and this dark rim on the side of the hole. But in this case, the rim is the same everywhere. I have no astigmatism in those two images. It's perfectly corrected. But this one is a bit strange, right? It looks like I'm in focus there and completely over focus at that position. And indeed, this image has a strong astigmatism. So this image is in focus, over focus, and I have some part over focus, some part in focus. If you look carefully, you will also see that the carbon film is not homogeneous anymore. It looks like maybe it has been stretched or whatever. You see elongated structure in this direction, which correspond to the direction of the astigmatism. Again, it's because I'm in focus in that direction and not in focus in the other direction. Okay, with this we have seen the main aberrations that are relevant to understand a transmission electron microscope. In the next video, you will see how we can take group of lenses, put them together and build a complete transmission microscope. But before jumping to this, I would like you to have a look at those links. They will explain you and show you that electrons are also waves.